Hello guys, welcome back. So here we have another question from GATE 2021 based on network theory. So a 100 Hz square wave switching between 0 and 5 volt is applied to a CR high pass filter circuit as shown. So this is the circuit. The output voltage waveform across the resistor is 6.2 volt peak to peak. So input they are giving from 0 to 5 volt and 100 Hz means it is 10 milliseconds time period. And output what we are getting? Some waveform with peak to peak value of 6.2 volt. Okay. If the resistor is 820 ohms, then the value of C is dash microfarad, round off to 2 decimal places. So these kinds of questions are common in lots of places including job interviews. So let us first try to discuss and approach this from the frequency domain point of view. Let's see how it behaves. Okay. So when you say square wave, if you take its Fourier transform, and here since it is periodic, it will actually be the Fourier series. So I'll consider one side. Here if you see 0 to 5 volt, it is non-zero DC value, right? So what is the DC value of this? Average of this, which is 2.5. So it has some DC component. And then where does it have the frequency component? The first frequency occurs at 100 hertz, right? So my first thing will occur at 100 hertz and at multiples of those. And if you actually take the Fourier series, you will see that the amplitude of this will keep on decreasing as 1 by n. So this is our input. So what does this system do? This CR system here, it is a high pass. So it will be something like this, right? In dB scale. So this will occur at 1 by RC. So this is omega I'm taking. So this is my corner frequency. So if you see here at DC, it will be 0, right? For example, this transfer function if you want, it is R by 1 by SC plus R. So this is SCR by 1 plus SCR. So it has a pole at 1 by RC and a 0 at 0 itself, right? So for DC S equal to 0, this transfer function becomes 0. So whatever DC component it has, at the output, it will reject it, right? So from that what you can conclude? So this 0 to 5 volt will not be there. The peak will occur such that the average value goes to 0. So here they are saying it is 6.2 volt. So that means that the output waveform will be such that the lowest peak occurs at half of this value, which is 3.1 volt, and highest peak will occur at plus 3.1 volt. So this is minus 2 plus 3.1 volt. Okay, so that is what you can get from that. So now depending on where this 1 by RC occur, some of these may also get filtered, right? So let us say all of these frequency components come at the output. Nothing is filtered, only the DC is filtered. Then how will the waveform look like? So it will have the same peak to peak, right? But only the DC component will be 0. So it will be switching between minus 2.5 to 2.5. This is when all of the frequency components come into picture. Now let's say only some these low frequency components are also rejected. Then how will the waveform look like? So let us start from 0. Okay, I'll take an input. So according to this, my input is something like this, right? 0 to 5. Now let me draw the output for the case when, let's say this 100 meg 200 meg are rejected. Okay, then what will happen? So here if you see, it is going from 5 volt to 0. So which is a very sharp transition, which means that here there are lots of high frequency components present. So since only low frequency component is suppressed, this is mostly because of the highest frequency, right? So this will come as it is. So this will come same like this. And then if you see, observe from here to here, this is staying stable, which means that here there are more low frequency components contribution, right? So what happens? So since they are suppressed, this will again try to go towards 0. And again, when once it reaches here there is again a jump. So what will happen? Again it will jump. So this jump, how much it will be? Here it is 0 to 5. So here also it should be 5 volt. Why should it be 5 volt? Come back to the circuit. So this is a C. So across a cap, what did we say? The voltage cannot change instantaneously. So if here the voltage is this much, and then at input I am giving a 5 volt jump, then it means that at output also there should be a 5 volt jump instantaneously, so that the effective voltage across the cap does not change, right? So that's why here also there is a 5 volt jump. So that is why if you see here, if this drop is some, let's say 0.2 volt, this point will be 5.2 volt, which is greater than 5 volt, right? So this 5.2 is, I'm saying, from this to this, the peak to peak. So that is why here also, if you see, it is 6.2 volt, which is greater than our input peak to peak itself. Okay. And this is for, let's say, 100, 200 is removed. Now with the same thing, here again it is going to follow the same. Right. Now if say I remove some more components, then how will it look like? Now the transition all, if you see, it will be very sharp. So here it is 0.2, right? Here it might go even lower, and the peak to peak will increase, right? So it will be like this. So if you go to the very high, if this pole is at very high frequency, then what will happen? This will actually come and settle to 0. Then again it will have a 5 volt jump, settle to 0, 5 volt jump, settle to 0, and so on. So now here if you see, it will have a 10 volt peak to peak. So maximum it can go to 10 volt. So this is for your high pass system. Same way you can also analyze your low pass system, okay, which will be comprising of R and C. So in that case, although your input is changing, since your cap comes here, your output cannot change instantaneously. So that is what you need to keep in mind. Okay, coming back to this question. So here, how will the output waveform look like? So it will have a jump here. In steady state I'm talking about. So it will go to some value. It will have this jump, come to this value, have a jump, and so on, right? And this value itself is 5 volt. And this is 5 volt. But this is minus 3.1. So then what will be this value? So this value will be 5 minus 3.1, which is 1.9 volt. So from here to here, if you see, this is a RC circuit, first order. So it should have an exponential settling. So we are coming back to time domain now. So this will be of the form of e power minus t by tau. And what is it starting from? It is starting from 3.1. So this is 3.1 e power minus t by tau. And we need to find tau, and then we can arrive at C. So now this is equal to 1.9. At what t? At t equal to, what is this? This total we said is 10 milliseconds. So this is just 5 milliseconds. So t equal to 5 milliseconds. So now we can solve and get tau. So e power minus t by tau is equal to 1.9 by 3.1. My tau is nothing but t divided by ln of 3.1 by 1.9. So this, if I take it to that side, I'll get ln of 1.9 by 3.1, but I have minus sign. So I'm just inverting the ln here, natural logarithm. So and t I know, now tau I can find. So tau is 5 millisecond by ln of 3.1 by 1.9. This we can use the calculator quickly. So this comes to 10.21 milliseconds. And we know the R value. And our tau itself is nothing but equal to RC. So C is equal to 10.21 milliseconds by R. R here is 820 ohms. And we want it in micro. So we can multiply by 1000. So what will this come to? So 10.21 divided by 820 into 1000. So this comes to 12.45 microfarad. So this will be our C value.